طيب، بسم الله الرحمن
Okay, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Did you check the homework that was posted? Okay, you can all access the Blackboard now, right? Good, great. The just a recap, just to recall that the idea of the homework is to guide you in your study. Okay, so the homework are not graded; they are only just for you to practice. Still, you can get also exam questions from these homework. Okay, so. You're strongly advised to solve each homework as soon as they're online because they're just a preparation for what comes next. The assignments to this week, inshallah, we're going to have the first assignment. They will be graded and you'll not have a solution for it. So the homework usually you'll have the solution later on a little bit. Sometimes they give you the homework with the solution. It's up to you to know whether you want to test yourself or not. Assignments, there will be no solution. Okay. Of course, with ChatGPT, everything now is good. It's easy to get the solution, but challenge yourself. Okay. So that's the whole idea. Let's start with a recap of what we discussed so far. Just so that you don't lose interest, we're still talking about robotics, okay, but it's a little bit delayed. So the whole idea, just so that you remember all of the spaces that, okay, most of the spaces that we find, most of the configuration spaces that we find in typical robotic systems, they don't have any Euclidean structure, okay, which means they don't have a vector space structure. This term, okay, will be clear today what we mean by that. And usually when we want to design, to study these systems, whether with analysis, whether to do simulation, whether to do control, and more advanced stuff, we find that these geometric methods become useful, okay? So they respect the fact that these spaces are not, okay, Euclidean. And today, inshallah, this will become a little clear what we mean by that, little clear, okay? This is what we covered so far. We said we're building in this first topic all of the mathematical foundations that will be needed later on, inshallah, throughout the course. So we started from very abstractly what a set is. And a set is simply just a collection of objects, and we define maps between these sets and so on. And then we said that a space is simply a set with some extra structure. And last time we looked at extra structure that we gave to a set, and this was in terms of this group operation, this binary operation that takes two elements of the set G and gives you another set, that takes two elements of the set and gives you a third one, and respects certain properties that we discussed last time, makes the pair of G and the operation what we call a group. Today we're going to be looking at something similar. We're going to be giving a set two more operations, okay, two different operations, and we're going to be, again, based on some conditions that we're going to be satisfying by these maps, we're going to be defining what's known as a vector space over a field. So this is the topic of today. A recap of what we discussed last time is that F, so this is F here denotes a map that has a domain A and a co-domain or a target space B. It maps X to some point F of X in B. So this is the picture that you should have in mind abstractly. Okay, so far the main thing, if you really want to understand these concepts, learn them abstractly without trying to find many examples. And I'll stress on this point today, inshallah. We said the map F between two sets can either be surjective, injective, or both, or neither. Okay, so you have all of these four options. Okay. Then we discuss what a group is, which is a set plus some extra structure, and this structure is simply given by this map, okay, that takes two elements of the set G and gives you a third one. We call it just a binary operation. Binary here doesn't refer to any zeros and ones in auto computer sense. Binary is just two elements. So this is the reason why then the notation and then you have these three conditions. Okay, the first one is that you satisfy it for all elements, and this is usually known as the associativity condition. The second one is usually known as there exists an identity element. And the third one is simply there exists an inverse element for every element that's in the group. And this is very important. Sometimes you can satisfy one and not the other. If you don't satisfy any one of these three, you can easily conclude that the pair that we're talking about is not a group. Okay, Another also check, which is some people asked about it last time, is that there is a fourth condition. Actually, there is a zeroth condition. You can think of it this way: that if I have some operation in mind and I give it two elements in G and I don't stay in G, which is known as the closure condition, then no need to continue with the rest of the with the conditions, because this is not even a group. Okay, we don't have this basic operation. Another terminology is that we said a group is the pair G and the operation is called abelian if it satisfies this extra condition. Okay, so this is the fourth one, or if you count this one, this will be the fifth condition. Any questions on what we discussed so far? Okay. Abstractly, okay. So these are the new information that we learned. Today we're going to be just like what we did with sets. We said that there's the set abstractly, and then we have maps between sets. We're going to do exactly the same. Now we introduce groups. Now we're going to be looking at maps between groups. Okay, and just introduce a number of notations. Question? Okay. So consider now two groups. The first one abstractly is G and its corresponding operation, and the other one is G is H and its corresponding operation. Okay, I'm not telling you what these operations are. I'm not telling you what these sets are. These are very abstract. Okay, so each one of them is a group, and if there exists a map, okay, rho that takes a G to H, okay, and also satisfies this condition, and you read this like this. So A plus B, where does this element live? So A plus B, where does this element live? In G. And rho can eat an element in G and give you an element in an H. Okay. If you calculate this, okay, this element, which will be an element in H, no, the result is an element in H. It's equivalent to first have rho eat the element A, which gives you an element in H, and rho eats the element B, which gives you an element in H. So I have two elements now in H. What can I do with them? I can act on them with the operation that's corresponding to H, not the operation that's corresponding to G. Okay, and I get the same result. If I do this for all elements A and B in G, then this rho is simply called a group homomorphism. Just a name. A group homomorphism. Clear? Clear for everyone? Okay. Now let's add another condition. If we have, in addition to rho that satisfies that, and it's also a bijective map, then we call rho a group isomorphism. Okay? So now you see the difference between a group homomorphism and a group isomorphism.
Bijective is both ways, yeah.
Bijective, we discussed it last time. Did you check it last? Okay. Okay, so watch it first before asking. Okay. So, but bijective, okay, so can anyone recall what the bijective map is? A surjective map and an injective map. What does that mean? Okay. Okay, so it means it's a one-to-one. So for every element in the domain, I have a corresponding element. Only one element in the codomain. And for every element that I hit in the domain, okay, so for every element that I hit in the codomain, okay, I can actually go to it. So I can go to all elements that's in the codomain. That's the idea of the surjectivity. If you satisfy these two, this means that the map is injective and surjective, which we called it the name bijective. What does that imply? There was something that came from this definition. That an inverse exists, exactly. So if I have a bijective map, then I can define its inverse that goes back, okay, from the codomain to the domain. So if I have a map that satisfies this condition and it's also bijective, then we call this a group isomorphism. Now, yes.
Can be a domain. This slide, group G is the domain and group H is the codomain
of the map rho. Right? That's the correct definition. Yeah. Okay. Remember, G and H alone are sets. Everyone agrees? So when I say G and H just alone, already I'm talking about the sets. When I talk about the pair, I already mean they are a group, okay? And this is, if you want to be very precise, always think about it like this. Of course, this is too much to handle, especially when we go to a vector space and we have 3 structures. When we go to more advanced stuff, we're going to have 4 and 5, tuples given for every set. So sometimes, okay, it's clear within the context, okay? So if we're talking about vector space and I tell you a vector space, or for example, when I tell you a group G, you should know implicitly that there's a map that comes with. If I tell you the group H, there's a map that comes with, and so on and so forth. Okay, so this is just the context and being precise. So far, we're going to be very precise so that everything is clear. Which one? The new line. The group isomorphism. Okay, the meaning is
equivalent group, right?
which one?
Before it was equivalent set.
You mean if there exists a bijective map between sets, we said that the both maps are. We did not say the word equivalent because equivalent means something else. What was the word we used? Congruent was the congruent. Yeah, that's correct, and that's actually the name of the symbol itself. And we said that they are isomorphic to each other. Yes, exactly. So we said that we have here something very similar. We have that if there exists an isomorphism between 2 groups, then we say that G and H are between brackets group theoretic. If you remove the brackets, you can simply say they are isomorphic to each other. Okay, so G is isomorphic to H. And again, we write the GRP here to indicate we're talking about 2 groups. Okay, can we have 2 sets that are isomorphic to each other as sets, but not isomorphic to each other as groups? Yes. So this is why we're emphasizing this. Can I have them isomorphic to each other as groups, but not as sets? That's a question. Think about it. Can we have 2 groups isomorphic to each other as groups, but not isomorphic to each other as sets? Why? The answer is it's not possible, but why? As groups, okay. And what are the 2 conditions? One of them is including what? One of them is what, actually? You're almost there.
Projective means they should be
Exactly. One of the conditions that we have a group isomorphism, it's actually the definition of what a group isomorphism is that the map needs to be bijective. So if the map is already bijective between the sets G and H, this means that they are already isomorphic to each other as set. Okay? Yes or no?
Yeah.
Okay. Yeah, that's the meaning. That's the intuition. Okay. I'm gonna come to that point today. Today will be a very painful lecture for you. Okay, so okay, but I'll come to that later. Is the definition clear? Okay. The only thing that I need you to use from your brains right now is only logic. Okay. Don't try to connect dots with anything outside. Okay, and I'll come back to that later. Okay, the connecting comes later, inshallah. An example, 2 examples. In today's lecture, we're going to have, I think, only 4 examples. Everything else will be abstract. Okay, that's what I'm telling you. Put all of the connections later on. Just take the new terminology, understand them one by one. Okay. So this is an example of a map between 2 groups. The first group is R and the plus operation. Remember last time we said that R and plus, they correspond to a group. If you remember from the examples we had last time. And R plus and multiplication, so the multiplication that you're all used to, okay, they actually also make another group. Okay, so that's left for you to try to check at home, whether that's true or not. So I have this group and this group. Okay? And I define this map as the normal exponential you're all familiar with. So I take one element in R and I calculate the exponential of it.
Definitions about plus greater than 0 or greater than equal to 0. Should I suppose or assume what is the definition?
you can deduce it from the map here. Can anyone say what this includes the zero or not? Why? No, that's not. Still, can anyone answer a slightly general more question? Sorry? Exactly. So the E of t cannot, okay, it has an asymptote zero, so which means that I can never calculate the exponential and get the zero. Okay, so this means that I'm talking actually about the r plus that doesn't include the zero in it. Okay, so that's implied.
Also, the co-domain itself, it doesn't have zero.
The zero, exactly. Yes, absolutely. There is a property of the exponential. Does anyone remember this property? Make sense? Does it recall? If you don't know this property, it's a property. That's it. Okay. You either saw it before or you didn't see it before. Okay. If I take the exponential of two numbers, okay, the addition of two numbers is equivalent to have first the exponential of the first one multiplied by the exponential of the second one. Okay. So because of this property, what does this look like exactly? You see, this equation is exactly this equation, provided that you think of this row as the exponential map, and the plus here is the plus between two numbers, and the multiplication here, which is the group that's given to the h, is the multiplication between two numbers. And thus this expression, if you want to look at it as an example, is exactly this one. Make sense? Okay. And because we have this, okay, property, what do we call the exponential map? A group homomorphism. Now another check. Is it bijective? Is this map bijective? Can I go back and forth? If I give you any number here, okay, positive number that does not include the zero, can you tell me which number it corresponds that will give me this number that lives in R? What do we call this map actually? The inverse. Then right, the natural logarithm. So the natural logarithm is exactly the inverse of the exp. Okay? So it is a bijection, okay, because the inverse exists and you already know what the inverse is. Okay, so both are related. And thus we don't call this just a group homomorphism, it's also a group isomorphism. So so true or false, every group homomorphism is an isomorphism. Every group isomorphism is a group homomorphism. Okay. Another example, two new groups with two new operations. The first one is the general linear group. Does anyone remember what the general linear group was? The set of non-invertible of invertible matrices. Okay, I think what you mean is that the set of non-singular matrices. Okay, so the set of all invertible matrices, okay, they make a group, and the operation that comes with them is simply the matrix multiplication, the normal one that you know, row by column, row by column, row by column. So this is one group. Another group is multiplication, but R excluding the zero. Is this R excluding the zero the same as this R plus? Why? Exactly. So this R plus, okay, so R, okay, has zero and positive numbers and negative numbers. Okay. R plus is all positive numbers excluding the zero and the negative. But R excluding the zero is simply all positive numbers, all negative numbers, and the zero is not included. Okay. And with this and the multiplication, we also have another group. And then we have the determinate map. You all know how the determinant is calculated? Okay. If you don't know, you just use MATLAB or something. Okay. The definition is is known, and you if you want to calculate it by hand, you can do it in a certain way. But the determinant, you can define it, okay, in the normal way that you know. And again, there's the property of the determinant that if I have the determinant of the product of two matrices, I can simply calculate it by taking the determinant of the first one, I get a number, and I multiply it by the determinant of the second one, and I get the same result. This is a property. You either know it or you don't know it. Okay? So because of this property, what do we say about the determinant map between these two groups? It's a group homomorphism. Is it a group isomorphism? Why not? So if I tell you I have the number 1, what's the matrix that corresponds to the number 1? There can be have many matrices. So that's an argument that the map is not bijective. Okay. And thus it's not a group isomorphism. This map is not injective. Yeah, it's not injective because I can start from many points here and I can go to the same number, right?
It is a standard notation, or I can define any set that has this property.
Written like this is a standard notation. It's defined like that. Let's write it here. Okay. And today we're going to have a more general object. It looks like it, but just I'm not going to be saying explicitly they are the same, but you can deduce that. Any more questions? Okay. So sets. So what we covered now is sets and maps between sets, groups and maps between groups. Now let's look at a new structure. We're going to have exactly the same drill. We're going to be introducing something extra, some extra structure with a set. And after that, we're going to be defining maps between this new structure. And this structure, what we're talking about today, is simply called vector space. Okay. So a vector space, another name for it is a linear space. And of course, when I say vector space, what's the first thing that comes into your mind? Euclidean vector space, exactly, which is Rn. Okay. But what we're going to be doing today is that we're going to be looking at them in a more abstract way. So Rn is an example of a vector space, but a vector space is much more than Rn. Okay. And I'm going to give you an example only today to confuse you, but I'm not going to be using examples more, okay, so that you can understand it at the abstract level. Most of this, okay, many of the concepts we're going to be discussing today are even applicable for infinite dimensional, okay, vector spaces, okay? So, and this you cannot have an Rn. So imagine you have a vector, okay, what you call a vector, and you have infinite numbers in it, okay? So a vector space is a set equipped with two operations, okay? So I have V, which is the set, plus, and I have the multiplication, okay? And it's not just a set of n tuples. So remember when we said we have Rn, it's just, okay, it's R times R times R times R, or the set A power n, or A, okay, with the superscript n, which means that A times A times A, which is the Cartesian product of A n times. But this is not a set of n tuples, okay? This by itself is a whole structure, okay? It's a new object, we're going to be calling it a vector space. Before talking about this vector space, we need to introduce another intermediate, okay, object, which is known as a field. So a field is also a 3 numbers, a set, and a plus and a multiplication. Okay? And they're defined as follows. So this is the definition of a field. And field, or between brackets an algebraic field, so some people call it an algebraic field, is a triple. So K, where K is a set, the plus and the multiplication, okay, which is here the plus and the dot, okay, which are maps that eat 2 elements of K and give you an element of K and satisfy the following. When you look at K and plus by itself, okay, and you take them together, you find that they make a abelian group, an abelian group. What was the difference between a group and an abelian group? Commutativity, exactly. If I take 2 elements of the group and I have the operation acting between them, I get the same result as taking the opposite, you know. So A plus B is equal to B plus A. This is an example of commutativity condition. Another, okay, condition that I need to satisfy is that when I have the K, the set K, and I exclude from it the 0 element, okay, I get an abelian group. The 2 maps plus and the multiplication, they satisfy the distributive property. What does the distributive property mean? It means that if I have the plus between 2 elements of the set K, and then afterwards I take the result. Where is this result? In K, which means I can multiply it by another element in K. What do I get? I get equivalent to first multiplying A by C, and then adding B multiplied by C. This is known as the distributive property. You can distribute the multiplication inside of the bracket. Yes. Yes, that's right. Yes. It's not explicit here, but yeah, that's true. And here is just when you're at home, if you want to recall what an abelian group is, okay? Given in this notation. Yes, Freddy.
Satisfy the first two conditions, but not the third.
Yes, of course. Yeah, that's possible in general, yeah. Okay. And everything is possible in mathematics. But what we're doing here is that we're having only the structure that we need. Okay. And if you want to generalize, yes, of course. And if you satisfy something and not something, you get a new structure that's called something else, and so on and so forth. So if you want to dive deep into this, you'll never get out. So that's why I'm only giving you the definition, in a very, as I said, I'm just spoon feeding you very few conditions, okay? With no offense, okay? Yes, they can be anything, yes. Yeah.
Space.
I have talked about vector space yet. I haven't talked about vector spaces yet. Well, this is only a field. Any questions about what a field is?
Excluding the zero, excluding the zero.
We defined before what does excluding an element of the map mean, remember? And the zero here, that's related to Ibrahim's question, that the zero is the identity element of the first abelian group. If I tell you K and plus are a group, which means that there exists an identity element, and this identity element here, you see, it's actually this one. It is the element that we call zero.
It's not the K, it's tuple.
Yes, it's K as in full. Which one? K plus and the multiplication, they are all together called the field. These are the conditions that these three should satisfy. So take these two together, they make a abelian group. Take this one, and because these two are an abelian group, there exists an element called the identity, and we're going to be calling it zero. So this is just the notation of the element. Does anyone remember what the identity element we called it in the previous lecture? E. So instead of calling it E, I can call it zero.
Condition satisfied, I have to.
Exactly. Absolutely. Yes, that's correct. Yes.
Say K, multiplication plus, is that okay? Instead of plus multiplication.
No, it makes a difference. Because then all of this, then this becomes the abelian group. So K and multiplication. And K excluding the zero and the plus, they become the abelian, they also need to be abelian, and so on and so forth. You're talking about something else. And it could be, in general, that these three together in this order are a field, but if you swap the plus and the times, I don't get a field. What? I'm talking about in general. Okay? Because these are two different operations, plus and multiplication.
And operation like in this one, K plus multiplication.
Yeah.
You swap between the multiplication and the dot, I think it might be the same.
You might think, okay, prove it. I'll give you an example to see it clearly. It's not the case. Let me see where's the example. Yeah, so this is the example that we have. Okay, so the set R. Okay, so these are all examples. The set R, the set Q, and the set C. So R was the set of real numbers, Q was the set of rational numbers, and C was the set of complex numbers. You all know that if I have two real numbers, I can add them and I can multiply them together. So we're talking about the normal multiplication, normal addition. If I have two complex numbers, I can multiply them together and I can add them together. Okay? And rational numbers, I can also do the same with them. An example of something that's not a field, I'll start with this one first and I'll tell you, okay, this idea of the reverse. So something that's not a field is actually the integer numbers with the plus and the multiplication. Which condition of these is not satisfied with it? The set of integer numbers. So set of the integer numbers with the normal plus and the normal multiplication. No, there is an identity. So the identity here is the 0, and the integer numbers, they have the 0. Okay, I'll give you a hint. It's in this condition. There is no 1 over, exactly. The multiplication here, integer numbers, they have only -5, -4, -3, and they have 5 and 4 and 3 and so on, and the 0 included. If I have excluding the 0, and I look only at 2, for example, I take the element 2. If 2 and the multiplication is an abelian group, this means that what needs to exist in this group? The 1 over 2. So the inverse, the multiplicate inverse here is different from the additive inverse. The additive inverse of 2 is -2. I add them together and I get the identity element, which is 0. But the multiplicate inverse, okay, doesn't exist in the set, which means that Z and plus and the multiplication are not a field, okay? Before that question, okay? So let's look at the real numbers with the plus and the multiplication and use this logic. If the plus is an abelian group, right? With the real numbers. But is the multiplication an abelian group if you have the real numbers? Now swap this, you see? If this is plus and this is multiplication, I need to exclude here the 0 for this to be abelian, because 1 over 0 is not defined. But if I have the opposite, where I need to have k and multiplication and plus, does it work? If that's the case, then the multiplication should be abelian, and the plus excluding the 0 should be abelian. So you see, this is clearly not the same field. It's actually not a field. Yes, ma'am.
Here, excluding again this, I can exclude any subset. And for example, if I have, for example, Z or R, R cross R, give me R. So the second condition here, rather than I say R, I say, for example, it will be N, and it is this N subset of R. Is it possible?
No, not clear what you mean.
Here we said that K excludes 0. So
yes,
this means that this invertible, it is subset of K itself.
That's right.
So can I say by this logic, for example, it is R, and here the second one,
yeah,
I believe with the subset itself.
Why?
Rather than R, it is
why? This is the definition.
Subset.
I'm telling the definition. So this is the definition. I'm talking about K, and I'm removing only the 0 element. That's it.
Only 0. I cannot exclude anything else.
Exclude anything else and call it something else. It will not be a field. That's what I'm talking. It's a definition. This is a field. Anything else is not a field.
But here it's because this is multiplication. If it is circle, for example.
What's a circle?
This
is another operation. You check. You check. That's what I'm talking about. So this is abstractly. This is the example. If I remove this example, what do you get? An abstract definition. The set K can be anything. The plus can be any operation. The multiplication can be an operation. I'm using the plus and the multiplication just to make it easier, but they can be something completely else. I can call it map rho and map gamma. And you define them in the way that you want. Yeah. If you're able to define them such that they satisfy this property, the triplet K and gamma and rho, they make a field. That's it. So this is an abstract definition. Today, everything will be abstract, which means that you can have weird things as long as you satisfy this.
But that definition does rho have to exclude 0 or not?
Rho.
Gamma and rho.
Yeah.
Does that mean that rho has to exclude 0? It will be gamma.
You mean the opposite, you mean?
Yeah.
No, plus and minus, replace them by A and B. So A and K are the abelian one, okay? And this one, which is B, the K itself is the one that has to exclude 0, not the operation. The operation, you cannot say that the operation excludes the 0. Exactly, excluding the identity of the first group. Yes, exactly. That's the better way to put it. Yes, Fahd. Yeah, exactly, yeah. So the 0 here, just to remind you, the 0 is the identity of the first group. Okay? That's it.
Now I get it, because I was just asking if we can swap the statements. But now I see that in the second one.
You require the first one, exactly. Of the first one, absolutely, yes. Okay. Actually, I should add it here explicitly. Okay.
The identity of the first operation.
Yeah. The identity of the first group, or to put it clear, the identity of this group. Okay. So now we need to, okay, we're gonna have the same drill, but I'm trying to do a bit faster. Okay. So now I'm gonna give you 3 new symbols. First one is called V, second one is circ plus, third one is circ multiplication. New set, new operation, new binary operation, and a new binary operation. Okay. Actually, this one is actually not even called the binary operation, it's just a map. This one is a field. This whole triplet is a field now. So a vector space is not defined on its own. You always call it a vector space over a field. That's why we were talking about fields so far. So a vector space over a field is the set V equipped with 2 operations. The circ plus that takes 2 elements in V and give you an element in V, and it's called vector addition. And we have the circ with the dot inside that takes 1 element in K and 1 element in V and give you an element in V, and we call it the scalar multiplication. We should satisfy many conditions, okay? So I'll just leave this for you to check at home. I'll just jump with the examples, okay? Now, what is the thing that we call a vector in this abstract theory? All elements of the vector space V, of course with its operations, is called a vector. So any element in V, first of all, if you have the operations satisfy all of these conditions, we call this triplet, we call it a vector space over the field K and its own operations. Okay? And if we take any element in V, we're going to be calling it a vector. Is the abstract definition clear? Is the abstract definition clear? You don't need to have any examples. You just need to look at the abstract definition. So if I tell you, is V alone a vector space? No, I need to define with it 2 operations, this one and that one, okay? Examples. The first one, I'm going to be defining over the field R plus and multiplication, which is the plus you're all, okay, you know from so long, and the multiplication you all know, okay, from even longer. I don't know which was longer, okay? And I'm going to be defining new operations for the set Rn. You all know what the set Rn is? It's R times R times R times R, so an n-tuple. And then I'm going to define a new operation that takes 2 elements of Rn and give me another element in Rn. How is it defined? I just take the first element and I add to it the second element. First element plus the first element. Okay, ith element plus the ith element, and so on. Clear? I'm going to be defining a new operation called the scalar multiplication, which takes a lambda from K. Okay? Remember here, we said that this circ multiplication takes an element from K and an element from V. So this is an element from K, where K here is the real numbers, and an element from V is an n-tuple. How do I define this operation? I'm going to multiply lambda by the first, lambda by the second, and so on and so forth. So I have these 2 operations. You can check that, okay, these 2 operations, they satisfy everything, all of the conditions that we had. Just to give you a glimpse that one of the conditions was V and a plus are an abelian group, which means that there should exist the identity element that I add to any other element and I get the same element. And this is simply here the 0 vector. Yes.
The space itself is a field.
Yeah.
So
Then it's a field over a field.
the space is over a vector space.
No, that's not defined. Okay. And what if there are many what ifs? So you have to stop yourself. Okay.
This means that each operation here, each operator here maps to the exact order here.
I don't know what you mean.
For example, here, circle plus,
Yes?
it maps to 2 plus. And here, the circle dot, it maps to 2 dot.
This is how we
So
define it.
is
This is how we define it. This is how we define it.
the order here is
No, no, no. It's a definition, you see? It's a definition.
outside of these operations.
No, everything is possible. You see, this is the abstract definition. I'm like a chatbot. I really have very limited, responses. Okay, so this is the abstract definition. Okay, you have to understand it on its own, and these are very simple examples. I know the simple examples, they don't, meet the generality of the abstract definitions, but they are true. Okay. Another example, yes. Someone have a question? So this is a very painful example. Another vector space over the same field R. I'm going to be calling this a green operation, green plus, and this is a green multiplication. They are different from this one, completely different. Okay. Why are they completely different? Because they act on different spaces. So here I have the set Rn, which is the vector space, the set underlying the vector space, and I have here the set of m times n matrices. I take this element from Rm times n, and I take this element from Rm times n, and I get this element from Rm times n. Make sense? This is how we define. And I have scalar multiplication, and I define it like this. And then what is the identity element of this? Is the zero what? Zero vector is the correct way of saying. Okay. Of course, yeah, you're saying, oh yes, it's a matrix. Yes, of course it's a matrix. And this is the zero matrix. So right now what you're seeing in front of you is that this is a vector space. And every element in this vector space is called what? It's called the vector. Okay. So from now on, forget about what you know what is a vector, okay, and what you call a matrix. Okay, because usually you're going to be calling this a vector. Right? Sorry, you're going to be calling this usually before you have this course, you're going to be calling this a matrix, right? But now I'm telling you the matrix is a vector. Okay. Okay. And it's correct. According to the definition, again, according to the abstract definition, a matrix is a vector, yes. It satisfies this vector space. But what is the vector space we're talking about? There are three things. They are the set of what you call matrices, which is just some numbers next to each other, and the plus and the multiplication. And now you have something here that's, I don't know if you see it or not. You remember last lecture we introduced the map called the vectorization? Does anyone remember what the vectorization did as a map? Sorry? It was the reshaping, exactly. It was taking an n tuple and just putting them side by side. As a set, it was bijective, right? I can go back and forth between them. You can test yourself now that, okay, we haven't talked about vectors, maps between vector spaces, but this vectorization map actually tells you that this vector space is the same as this vector space if you define it properly. Okay, they are the same. Anything you can do with this one, I can do with that one. Okay, they are okay. At least as a set, with last time we said they are bijective to one another. But as I said, as a whole vector space, we're not okay. We do not talk about at all about maps between vector spaces, and this is what we're going to be doing now. So what we did for a set is that we defined maps, and then we said if these maps can go back and forth, okay, then they are called bijections. And when we have a group and we have maps between two groups and we can go back and forth, we call them group isomorphisms. We're going to be doing exactly the same. We're going to be looking at two vector spaces over the same field, and we're going to be defining maps that go back and forth between them. Okay, we're going to be calling them linear isomorphisms. And similar to when we wanted to have a group homomorphism, we need to have a certain condition that respects the group structure. This is exactly how you say it. The group condition, the condition for a group homomorphism respects the group structure. Linear maps will be exactly the maps that respect the vector space structure. So this is, okay, just an outline of what we're going to be doing now on the board. Yeah. definition. Linear map between vector spaces. So what is the definition of a linear map? So let the triplet V circ plus circ times and W square plus and square times be vector spaces over the same field K. And when I say K just like that, I mean there's its own plus and its own multiplication, but it's just, suppressed in the notation. Now, we say the map F from V to W is a linear map. Okay, this is our definition. It's a linear map if, and of course we need to satisfy some condition. So F is a map, it needs to eat what? F needs to eat what?
W and V.
Element from W and give us element of V.
Is that what VF does? It eats an element of V. Okay. I'm gonna write an element in V now and check for yourself whether this is correct or not. If I take a gamma and I multiply it by V1, is this an element in V? Where? Okay, so gamma is in K and V1 is in V.
This is in V, yes.
Everyone agrees? Okay. And then I'm gonna add to it another element V2, where also V2 is in V. Make sense? The result I get is equivalent to first eating V1. What do I get?
W.
An element in W. I don't get W, I get an element in W, which then I can multiply it by the gamma, with which operation? The square dot. What is the result I get? An element in W. What can I do with an element in W? I can add to it another element in W, which is f of V2. And this is defined for all gamma, so for all lambda in K, and for all V1 and V2 in V. And this is the definition of a linear map.
Have time to explain why this specific notation, this specific sequence of operations.
That's exactly what I just said. I'm gonna repeat exactly. Go back home, repeat the video. I'm gonna say exactly the same. That's why I have the video to me. Okay, can hear it 10 times. I'm not gonna change it. I'm like a chatbot. Okay. There's nothing else than this. I'm saying is defined. So definition. That's definition. You've seen this many times before, but in a much different way. You've seen it like this. Usually, you say a linear map is something that satisfies this condition. Have you seen this before? Usually. What's an LTI? What's a system? What's a system?
Linear, any linear.
Any linear what? Okay.
Generally, we call it one of the conditions for superposition. It's one of the
Superposition. The superposition condition. So what is the superposition condition? Is what makes a map a linear map. Okay. But has nothing to do with time invariance, has nothing to do with systems. Okay. Later on. Yes. Sorry? F of V2. Yes, please. Thank you. So F of V2. Yes. So yes, of course, we can always write it like this, provided that you know which operations you're talking about. Okay. But you have to look at it, once in your life like this, so that you can appreciate, how much structure there is behind it. And of course, when you're writing your own, when you write your own document, if you already know which operations you're talking about, just suppress all the notation. So this is, very heavy notation, just, to see really what's beneath this simple equation. Okay. But after that, you don't need to rewrite. You don't need to introduce all of this intermediate, all of this notation, all of these maps, and so on and so forth. Okay. So this is the definition of a linear map. Now let's have another definition, which is what is a linear isomorphism between vector spaces. Come on. Has to be one-liner. What is a linear isomorphism between vector spaces? A bijective linear map. So if F between V and W, assuming that V and W are vector spaces, is a linear map and bijective, then we call, and you see here what we mean by call, it's a definition. Any map that satisfies these two conditions, we call it a linear. Let me write this. We call it a linear isomorphism. Clear? Okay. Now I'm gonna define what's known as the set of linear maps between vector spaces. Now I'm gonna give you a set of maps. A set of maps. Okay. So each element in the set is what? Is a map between what? Between two vector spaces, exactly. Okay. So keep that in mind. What we're gonna be defining right now is simply all of this is a notation for the set of linear maps. So this is the set of all linear maps. Okay. Each linear map, I'm gonna be calling it alpha. Let's not use alpha. Let's use A. Okay. So A is a map between V and W. So A is a map between V and W such that A is a linear map. Instead of writing it like this, I could have added all of the conditions we had earlier. So I can put all of this inside of the definition, and we're gonna have, one huge definition of what the set is. But if you know exactly what the definition of a linear map is, then you can simply add it like this. You can say A is a map from V to W such that A is a linear map. Now, some confusion. Okay. This set, I can make it into a vector space. Okay. So we started by a vector space and another vector space. And we looked at maps between vector spaces. Make sense? And I said that this is the set of maps between all of the maps that take you from the vector space V to the vector space W is actually a set. Okay. And now I can make this set into a new vector space. How is this vector space defined? So I'm gonna make L, V, comma, W. What is this? What did I just write now? It's the name of the set. The name of the set. Another way, actually, you're gonna be seeing it usually, it's written is given the HOMVW. This is another notation. Oh, no. Whiteboard. Yeah, so this is another notation. Another notation, which means that it's another name, another symbol. I could have called it X, I could have called it Y, could have called it Ahmed. Exactly, nothing changes. So all of this is just the name of it. And I can give it some plus and some multiplication. This plus, okay, let me, so that you don't get confused. So this is a new plus, and this is a new multiplication. They have nothing to do with what we had before. And I can define it like this. Recall that an element here, okay, so A and B can be in this set. Okay, so they can be in L, V, and W. Which means A on its own is a map from V to W, and B on its own is a map from V to W. So if I want to define the plus between the two maps A and B, how do we define it? What is this? Where does it live? It lives in L. Exactly. Go back here. Okay, we had it in the slide, so now it will take us some time just to go back to the slide. But okay, check at home that the operation here, it takes two elements from the vector space and gives me another element in the vector space. So these two together, they make a new map. And if I have a map, what can it eat? It can eat a U in V. Before that, does this make sense for everyone? I took a map from this set, okay? I took another map from this set, and I combined them together with this operation. What did I get? A new map in the set. Okay? And this is because it's a map, I can act on any element in V and give me an element in W. Because now I have an element in W, this is exactly the same as A of U plus B of U.
Plus is the operation of V, right?
So actually, this is not correct. I need someone to tell me what's the correct operation to put here. Let's go back. So should it be the plus with a circle, the plus with the square, or the plus with the triangle or the diamond? Who says rectangle? Some people are still processing, so let's wait. So always check where are we right now. If A it's an element U that lives in V, where am I right now? If I'm in W. And if B it's an element from V, where does it go? To W. So I have two elements in W now. What can I do with them? I can add them with the operation that corresponds to the W. Okay.
Not have to make it necessarily so complex by calling it map and map. We can just say it's an element in L, it's an element in L.
What is this element?
Define that L is a set of maps.
Yes. So what's an element of that set?
A is a map in L, right?
Yeah.
So far we have been saying that A is an element in, let's say, L.
Yeah.
So why just
What is that element?
Every element is a map.
no,
Every element is a map. Yeah.
I'm saying keep repeating the point that this is a map and then we are going to a map, it becomes necessarily complex to process. That's what I'm saying.
Is it correct or no, it's up to you. Sorry? That's right. Yeah, you can do that. Yeah, exactly. Okay, so you can keep on. Okay, well, we can stay 1 more hour just to show this simple condition. So I leave that. I'm gonna give you some online material if you really want, to go into details.
Run out of symbols, the diamond and the shadow.
That's right. That's absolutely. Yeah, absolutely. That's correct. Yeah, but is it well defined? That's it. So that's what I'm saying. You need to do it at least once in your life, and you're familiar with it, and so on. Okay. Or if you're starting something new, for example, like what I said, Mohammed, I want to try something else. So you need to make sure, okay, you're not confusing what the different symbols are. Okay. So this is one condition that we need to satisfy. The second one, I'm just gonna write it immediately, and you can check for yourself that A, okay, multiplied by the A, which is this multiplication, is equivalent to A with this multiplication multiplied by AFU. Okay. So these are the two conditions that will make this one, the small a is, no? In the field, exactly, absolutely. So all of these three together, they are actually make a vector space on their own.
Over the field K.
Over the field K, absolutely, correct. Over K. Yes. A, this one should eat you, yeah, absolutely. Thanks a lot for. So all of this is a map, and I should eat the U. Yes. Sorry? Blue is not clear. Let's make it yellow. By the way, I forgot to introduce. So Farouk is your new TA, okay? So that's why he's. So that's his job, actually, okay? Just to correct. So let's see how much time we have. Okay, we have 5 more minutes. Let's see what you will cover. Okay. I'm gonna give you 2 definitions very quick, 3 definitions very quick, okay? Like lightning definitions, okay? First definition, okay? I think this is number 4. Yeah, 4. Oops. So there is something called an endomorphism. Okay. So let V be a vector space. And when I say this, I already imply there are some operations with it. And I also imply that there is some field that comes with it. Okay. So you can always, generalize this. So an endomorphism is a linear map that goes from V to V. Sorry. That's it. Easy. So all of the linear maps we had were between 2 different vector spaces. What is an endomorphism? A linear map between the same vector space. That's it. Yeah.
Same element in the vector or
The same vector space. It can eat any element, okay, and then go to the same vector space. Okay. Closure, I you have to be very careful with just using this. Okay. Intuitively, yes. I ate an element and I stay in the same, same set. And we can define the set of all endomorphisms with this symbol, and it's simply L of V. Does this make sense to everyone? It's a definition. What was this? The set of all linear maps from V to V. And now we just call this the set of endomorphisms over V. That's it. So every map here is from V to V. Okay. I'm going to define a new definition. So an automorphism is defined as the set of all endomorphisms where A is isomorphic. Make sense? Exactly. So every element in this set is a map that is both linear between the vector space V and V, and also bijective. Okay, can go back and forth between V and V. Okay, I will say it again. So every element in this set is a map from V to V that is linear, because we're talking about vector spaces V, and it's also bijective. So I can go back and forth. Every element in the endomorphisms is a map that is linear between V and V, but not necessarily isomorphic. You have to say it like this, because I could take an element in the endomorphisms, I can find sometimes it is isomorphic, sometimes it's not. Okay. Question? Good. So now let me give you some, okay, again, lightning statements, okay, that will take us, days to prove. Okay, not days, maybe some hours. Okay, we don't have that. So we said, I just showed you very quickly a sketch of how the set of linear maps between V and W can be made into a vector space. So it has a vector space structure, provided its operation that we discussed. I can make it into a vector space. Endomorphisms, okay, can they be made into a vector space or not? Okay, so let's go back. We said that I have a big set that consists of L, V, and W, and I have a smaller set. Okay, so you can actually picture it like this. So I have a very big set that we call it L, V, and W. And inside of it, there's actually a subset that we call the endomorphisms on V. So any element here can be a map from V to W, but any element from here is only a map from V to V. So I excluded many of the bigger set. And then if I go inside of here, I also I can have a map that's isomorphic or not, and I can constrain myself to maps that are only automorphisms. Okay, so an element here has to be bijective and also a linear map. It has to be linear isomorphism. A map here can be should be a linear map, but can be isomorphic or not. And a map here can be between two vector spaces. Okay? So if this one can have a vector space structure, and endomorphism is simply V and W, so W equal to V, so this means trivially that, I can also make it into a vector space structure. Okay. Now automorphisms cannot have a vector space structure. Now think about it.
You say that it has vector space, but a subset of it can't have vector space.
Huh? That's exactly the point. Think about it. What do I need to have a vector space structure, okay, on the set of automorphisms?
You need the field? No, all of the time.
You need to have something related to that. You need to have the inverse of the map. Okay? You need to have the inverse of the map. Okay? This will be clear next time. So I'll just say it right now. I'm not going to go to the details, but I'll just, okay, have it like this.
How can the set be isomorphic, but the subset? How can the set be a vector space, but the subset of the whole thing is not a vector space?
That's a very good point, because in this picture that you see here, they're all sets. Is any one of these a vector space? What is the picture I have here? Sets. For this to be a vector space, what does it need? It needs the operations that made into a vector space. So yes, I can make this into a vector space by giving it its corresponding operations. Yes, I can make this into a vector space by giving its corresponding operations. Will make so. But this, keep on looking. The same operations that make this into a vector space cannot make this into a vector space. Next time when we have a concrete example, this will be 100% clear. Just one, okay, so if you're not confused yet, let me just confuse you one little bit. Okay. Automorphisms, remember they are maps, right? Remember we discussed before the circ, the composition between maps. I can have a map that goes me from A to B, and a map that goes me from B to C, so I can have a composition from A to C, remember? So this composition, along with the automorphisms, we're going to actually call them as the group general linear group over V. So these are called the general linear group over V. And they are a group. So to rephrase, the automorphisms, I cannot make them into a vector space, but I can make them into a group. Endomorphisms can be made into a vector space, but not a group. And the linear maps from V to V to W cannot be made also into a group. And more on that next time, inshallah. Yes. On the operation circ, yes, which is the composition. So this is the operation that takes the composition of maps. Okay. So I have two requests. Please, okay. Do the homework if you didn't. If you didn't watch the first two lectures, this is okay. This doesn't make any sense to you today. Okay, so if you didn't watch it, rewatch the first two lectures along with this one, and sleep well tonight. Okay, study well tomorrow, so that when you come to Tuesday, because we're going to be building on all of this. Okay, if you don't study this part, Tuesday will be okay. We'll get complete lost. But I hope, okay, I promise, inshallah. Okay, if you study this on Tuesday, everything will be clear. Okay, so jazakumullah khair.